Let's continue our exploration of polygons by looking at quadrilaterals and the very much related parallelograms. Quadrilaterals, a couple things we need to know about what a quadrilateral is. We had triangles, tri meaning 3, now we have quadrilaterals, quad meaning 4. So a quadrilateral has 4 sides and 4 angles. Does not matter what the shape looks like, these are all quadrilaterals. They have more detailed specific names as we move forward, but for now we need to know that there are 4 sides to each quadrilateral. The interior angles, the sum of all interior angles in a quadrilateral is 360 degrees. Think about squares and rectangles as the basis for why this exists. If we have 4 right angles in the corner, that's going to be 4 times 90, 360. You can also think of a quadrilateral as 2 separate triangles put together. 2 triangles, that's 180 degrees each. 2 times 180 gives us 360. So all I need to remember is that angles 1 through 4, when I add them up, I get 360 degrees. I can set this up each time to find missing angles. All have 4, so I can just substitute in. I need to know at least 3 of the angles to find the 4th. Let's try a couple examples using what we know about quadrilaterals. So we have, in this case, 4 angles, 3 that are given, 1 that's unknown. I know that the sum of all interior angles of a quadrilateral gives us 360 degrees. So I'm going to add them all up. 110 plus 70 plus x plus 110 equals 360. Now it's just a matter of solving for x. I know that x in this case represents one of the angle measures. You could use angle 3 if you feel more comfortable writing that in. X is just always a great variable, a great placeholder. So I'm going to combine like terms. I get 290 because 110 plus 110 plus 70 gives us 290. And it's a one-step equation. What's happening to my variable? I'm adding 290, so I'm going to subtract 290 from both sides. Now I'm left with x equals 70 degrees. In example 2, we have a different quadrilateral. We're given 3 angles that are just single values, and 1 that's an algebraic expression. In this case, x is a value within that expression, an unknown within the expression. All 4 of those angles still add up to 360 degrees. So I can use that same exact 95 plus 93 plus 87 plus 27x plus 4. I added the 3 given angles plus the 4th, which is an algebraic expression. In this case, keep in mind, what does x stand for? X does not stand for a full angle measure. It stands for a variable within an expression that represents an angle measure. 27x plus 4 equals something. So I'm going to solve for x first. I'm going to combine all my like terms. 95 plus 93 plus 87 plus 4 gives me 279 plus 27x. That didn't combine with anything. Now it's a 2-step equation. After I combine like terms, I always need to determine, is it 1 or 2 steps? Here it's 2. So I need to ask myself, what's happening to my variable? I'm multiplying by 27, and then I'm adding 279. I need to move in the exact opposite direction using inverse operations. So inverse direction, inverse operations. I'm multiplying by 27, adding 279, so I need to subtract 279, and then divide by 27. 360 minus 279 gives us 81. 279 minus 279 gives us our identity of 0, so that's why we have 27x by itself. Now I need to divide both sides by 27. 27x divided by 27 gives me just x. 81 divided by 27 gives me 3. Keep in mind, what does x stand for in this case? It's a variable within an algebraic expression. Now there will be questions that ask you in this case, solve for x. And those questions, I've already solved for x. I'm done. However, some questions may extend, and they may say, what's the angle measure? What does 27x plus 4 equal as a degree measure? So I substitute my x back in. 27 times 3 plus 4, so that's 81 plus 4, that's 85 degrees. If I wanted to double check this, 95 plus 93 plus 87 plus 85 does in fact equal 360 degrees. Parallelograms are a special offshoot of quadrilaterals. They're quadrilaterals that are composed of two sets of parallel lines. So before we even look at the shape, imagine two sets of parallel lines. The green lines are parallel to the green line, the red lines parallel to the red line. This gives us two sets of transversals that are cutting two sets of parallel lines. Knowing what we know about parallel lines cut by a transversal, we can start to understand some of the concepts involving the angles. So let's take that shape right there. Opposite sides of this parallelogram are congruent, so they're the same size, and they're parallel. So we can mark those. Those two are congruent, they're the same measure, and those two are the same measure as well. Since we're dealing with parallel lines cut by transversals, we can also establish that these angles are congruent. The opposite angles are congruent. So these two are congruent. These two angles are congruent. So if I'm given a parallelogram, and I know it's a parallelogram because it would tell me that its opposite sides are parallel, I can automatically assume if I have one of my angles, I know the angle opposite to it. If I know one of my sides, I know the side measure opposite to it because they're congruent. The same properties for quadrilaterals work here as well. If I add up those four angles, it's still going to equal 360 degrees. But because I have parallel lines cut by a transversal, I know that something else is true. What I see here are sets of same side interior angles. So those are supplementary. So I know that 1 and 2, they're going to add up to 180 degrees. 3 and 4 will add up to 180 degrees. 1 and 3, 180 degrees. 2 and 4, 180 degrees. So this is just another way to help you find an unknown angle. So in the case of a parallelogram, you can find all four of your angles if you just know one angle. We can also look at a lot more with parallelograms if we look at their diagonals. Diagonals are line segments that connect opposite angles in a quadrilateral. So they cross diagonally from one angle to the opposite angle. It essentially is breaking the parallelogram or quadrilateral into four different triangles. The diagonals in the parallelogram bisect one another. That means, think about the word bisect. Bi, two, sect, sections. It breaks it into two equal sections. So that means that these two line segments are congruent. They're the same measure. If one is 5, the other's 5. These two are congruent. They're the exact same measure. If one is 6, the other's 6. Let's go back to the example of the parallelogram we looked at earlier. We have the same angles, 110, 110, 70, but we don't know what x is. There's a couple things we could do. We could take its supplementary angle, so either the 110 to the right or the 110 above it. Those two angles, when you add them together, have to equal 180. So 110 plus an unknown variable equals 180. We solve by subtracting 110 from both sides. X still equals 70 degrees. Now I only know this works because I was told this is a parallelogram. You'll either be told it's a parallelogram or you'll see parallel markings on the sides of the parallelogram. I could have also noticed that the angle opposite the x is 70. So this is 70 degrees, which means that x is 70 degrees, And that's how we get our answer, 70 degrees. We can also assume the same thing. The opposite side is 3 inches, so this side is 3 inches. The opposite side is 4 inches, so this side is 4 inches. If I'm not directly told that it's a parallelogram and I don't see parallel markings on the sides of the quadrilateral, I can look at the measurements. If I see that opposite angles are congruent and opposite sides are congruent, I'll automatically know that this is a parallelogram. Let's look at this parallelogram. In this case, I know it is because it has the markings. Those little arrows tell me that the opposite sides are parallel. If all pairs of opposite sides are parallel, that means they're also congruent, means I have a parallelogram. If AD equals 10, then AE equals something. In this case, we're looking at the diagonals. AD and CB are diagonals. They bisect each other. They cut each other in half. So if I know that AD is 10, half of AD is 5. So AE is 5. ED is 5. CB, the green diagonal, is also bisected. It's cut in half, which means CE and EB have to be equal, have to be the same. Since CE is 4, EB also has to be 4. So that means CB is 8. If I know the measure of one of the bisected lengths, in this case CE, all I have to do is double it to find the total length of the diagonal. Since AC is 6, BD also has to be 6. Now in this case, AC is one of our sides. We know that all sides are parallel and congruent.